Hi everyone, my name is Pei-Hsin Liu. Today I'm going to present a new interleaving method for adaptive constant control in multiphase VR entitled Hybrid Interleaving with Adaptive Phase Lock Loop. At the beginning, I will introduce the issue of two state-of-the-art interleaving methods. One is pulse distribution method, another is phase lock loop method. Then I will show you our small signal model to identify the stability problem of using phase lock loop, and then propose the adaptive phase lock loop to solve the issue. After that, I will present a hybrid interleaving structure to further simplify the circuit complexity of using phase lock loop method. Finally, I will demonstrate the test bed and the experimental result to verify our model and propose the interleaving structure. Constant on control has been widely used due to good line load efficiency, fast transient, and enabling high bandwidth design to eliminate output bulk cap. However, since the on time is fixed, the switching frequency can change widely under input and output voltage change. For laptop VR as example, the duty cycle can change between 0.06 to 0.4. If the switching frequency at D equal to 0.06 is 800 kHz, the switching frequency can increase to 5.3 MHz at D equal to 0.4. In the end, it may cause the thermal issue and very difficult to achieve good interleaving. To solve the issue in multiphase, first method called pulse distribution structure. In the left-hand figure, the input and output voltage are sensed to the on-time generator of each phase. Then, on-time is slowly changed based on the ratio of the two. Therefore, when duty cycle increase, T-on will increase to remain 800 kHz region. Next, to achieve interleaving, a phase manager is used to distribute the pulse D sum to each phase. The bottom right figure shows the first pulse of D sum goes to D1 and second pulse to D2, so on and so forth. And the modulation of D sum is based on the intersection between summed inductor current I sum and the control voltage Vc. Since the frequency of I sum is 2 times of switching frequency, so 180-degree phase shift is automatically achieved. And this method is very simple and has been widely used. However, if you look at the transient response, when Vc has dynamic due to the state upload transient, the modulation scheme makes the PWM signal of two phases unable to overlap immediately. So the first issue is slow transient. Another issue is noise sensitive. The ripple cancellation diagram shows that when duty cycle operates at 0.25 for 4 phases as example, the I sum ripple is gone. So any small amount of noise on I sum or Vc can change the intersection point and cause severe duty cycle jittering. And besides, jittering becomes even worse and even severe in higher phase number. To overcome the limitation of first method, phase lock loop structure has been proposed. To remain 800 kHz switching in wide duty cycle range, the phase lock loop adjusts the on time of each phase to track a fixed frequency clock signal F clock 1 and F clock 2. And then the interleaving is achieved by phase shift the two fixed frequency clock in 180 degree. The modulation of D1 and D2 is determined by the intersection between the individual inductor current and control voltage. So the first advantage is less noise sensitive than first method. Besides, when the transient occurs, D1 and D2 can overlap naturally, so the transient response is faster. However, you can see in the left-hand circuit there are multiple phase lock loops and multiple high-speed comparators. They will increase the circuit complexity. Also, the PLL loop compensation is not easy to design, and we'll discuss in the next slide. This figure shows a typical implementation of PLL loop for constant on control. The on-time generator is built with a ramp SR compared with an on-time control voltage V-on to determine the on-time width, and V-on is generated by PLL loop. Now, let's consider a scenario where the initial switching frequency, FSW, is higher than the clock frequency, F clock. So, in the first stage of phase lock loop, the PFD, called phase frequency detector, will check the rising edge of two signals and identify the frequency difference, then generate a pulsating current signal, IPFD, which width is equal to the difference. After that, the low-pass filter, or PLL, smooths out the pulsating signal, IPFD, and converts into an incremental V-on change. When V-on increases, the switching frequency will become lower and lower and eventually approach to clock frequency. The speed of V-on change is depend on the bandwidth of PLL loop, called TP. And let's take a look at the actual V-on waveform in simulation. And it shows an oscillatory response both at high TP bandwidth design like 90 kHz, so as very low bandwidth design like 500 Hz. This result indicates that the potential stability problem of the PLL loop for constant control. Unfortunately, there's no model to figure it out. Therefore, I proposed a small signal model to understand the issue and provide design guideline. During the modeling process, the nonlinear components inside the loop are treated as a single entity. Then, based on the describing function method, V-on to IPFD transfer function is derived. The simplified model shows it contains an original pole. Then, the transfer function of low-pass filter contains an integrator to correct error and the low-frequency zero to boost phase, and the low-frequency pole to filter out pulsating current. TP is the product of the two transfer functions. And the body plot of TP shows the phase characteristic start at minus 180 degrees because of two original poles. Then phase increase higher than 45 degrees when frequency higher than the zero. After that, phase drop below 45 degrees again because of low frequency pole. It indicates that there's a narrow frequency region with sufficient phase margin higher than 45 degrees. So TP bandwidth need to be carefully designed. If the bandwidth is designed too high or too low, insufficient phase margin causes oscillatory response. This model also tells us the bandwidth can vary with the duty cycle change. When D equal to 0.06, bandwidth is crossover at peak phase margin, but when bandwidth at D equal to 0.4, bandwidth slide out of the stability zone. Therefore, the bandwidth variation makes the compensation difficult. To simplify loop compensation, adaptive PL loops is proposed to remain constant bandwidth over wide input and output voltage change. The model points out one way to fix the gain is to make the ratio of ID over SR and duty cycle is constant. In other words, the ID need to be proportional to VL, SR need to be proportional to Vin. In the example implementation, the magnitude of internal current charge pump of IPFD is controlled by VR, feed-forward through a simple current mirror with K1 gain, while SR is adjusted by Vin feed-forward through a RC network tightened to Vin. Proposed model and the adaptive loop concept is verified in the experimental platform with the console controller from Texas Instruments on the motherboard and one adaptive PL loop on daughter board. The experimental result of TP loop gain shows that it agrees with our model very well, so the model is very accurate. Then the TP loop gain of adaptive PL loop shows that the bandwidth always anchored at 9 kHz with peak stability margin of 90 degrees over wide duty cycle range. So proposed adaptive idea is effective. When proposed adaptive PL loop is plugged into the PL loop structure, the design complexity is resolved. Next step is to simplify the PL loop circuit. And my strategy is utilize the phase manager inside the pulse distribution structure to simplify the PLL loop structure. This slide shows the concept of hybrid interleaving. The magnitude ratio of I sum to individual current IL1 indicates that there's no ripple cancellation point within the intrinsic duty cycle range for two-phase operation. Based on this understanding, let's see how we can simplify the PLL loop structure with 4 PLL loop and 4 high-speed comparators. First, the pulse distribution structure is applied to every two phases. Since the modulation is determined by I sum of two-phase current, so the jittering due to the ripple cancellation issue is skipped. Besides, the phase manager automatically provides 180-degree phase shift between phase 1, phase 2, as well as phase 3, phase 4. Then 2 PLL loop can be removed. So finally, the circuit might be much simpler since it saves 2 PLL loops and saves 2 high-speed comparators. The transient performance of hybrid interleaving is faster than pulse distribution method because the PWM signal between two pulse distribution groups can be overlapped naturally during transient. Besides, the transient simulation in Simplex is performed with state-of-the-art field model of laptop VR and based on the low transient spec of VR 2.5. It shows that the proposed interleaving structure has comparable transient performance with PLL method. Here is the experimental platform. The top side PCB contains 4-phase buck converter, 2 phase in here, another phase in here. Also, there's a constant controller from Texas Instruments. The bottom side of PCB it connects to a 2 daughter board, and this 2 daughter board is used to implement the adaptive PLL loop circuitry. The 2 PLL loop will work with the 2 phase manager inside the control chip to construct the 4-phase hybrid interleaving. To demonstrate the benefit, let's compare with the motherboard on the right-hand side with low bandwidth design around tens of kilohertz. We can see there are multiple bulky output SP cap is needed to meet the AVP requirement. Then, after apply our interleaving method with high bandwidth design as shown on the motherboard on the left-hand side, the bulk cap has been removed and replaced by some decoupling cap outside of the socket. Let's take a look at the transient performance. I pick up 2 PWM signal as example to show the overlapping feature. When the transient occurs, you can see D1 and D3 are overlapped immediately. And then when the transient is settled, and the D1 and D3 will go back to 90-degree phase shift. The overlapping feature allows the inductor current provide the energy to the load immediately, so you can see no undershoot on output voltage. Second, let's take a look at the steady state waveform at duty cycle equal to 2.5, which is the ripple cancellation point of total inductor current for 4-phase operation. You can see the PWM signal not only perform correct interleaving angle, but also exhibit stable PWM signal without jittering. Let's see the small signal property of hybrid interleaving structure. The major loop gain of constant control loop shows this structure enable high bandwidth design over 120 kHz. The benefits of high bandwidth design shows in the reduction of output cap. Thanks for your attention. If you have any further question, please feel free to contact me. See you next time.